Hi everyone. So today we're going to talk about statistics and variables and talk about the different types of variables that you might encounter and why it's important to understand which type of variables that you're dealing with. So to start out, statistical methods allow researchers to explain and understand variation in data. And an important first step is to describe this variation in the data so that you can potentially adjust for it in your analysis. So in order to use the tools of statistics to do this, first you need to understand what the different types of variables are and eventually how you can build models to describe these variables. So in general, there are really two types of data that we'll encounter. So the so-called quantitative and qualitative data, and the type of data that you're dealing with is crucial in order to determine what are the proper techniques that you can use and what are the proper estimation and hypothesis testing techniques to use on certain types of data. So in bullet 2 I have a couple of questions that you may encounter in your clinical research when you're trying to look at associations or certain things. So should you use a t-test? Should you use an ANOVA? What about a chi-square test? Should you use a nonparametric test? So understanding the data types that you're dealing with is critical in order to answer these kinds of questions. So what's a quantitative characteristic? Well, a quantitative characteristic, so as an example, could be a measure like blood pressure or serum sodium levels. So this type of variable contains information about quantities, so actual numerical values that mean something. A qualitative characteristic is a characteristic that deals with a quality. So for instance, if you had a variable that indicated what type of pet an individual in a study had, let's just say cat, dog, or fish. So I'll underline these. So cat, dog, or fish, those would be the possible values that a qualitative variable could take. And these deal with information where really a numerical value doesn't signify anything about the value that the variable takes. So for instance, in bullet 3, I wrote that it's common to assume a number, a qualitative, or excuse me, a quantitative number to these categories. So for instance, I've assigned cat to have value 1, dog to have value 2, fish to have value 3, but essentially this is just a numbering to distinguish categories. The numbers 1, 2, and 3 have no quantitative meaning. They're merely categorical. So in statistics, as you'll know from the last lecture, we talked about variation. So statistics really is a study about things that can vary, and importantly, can randomly vary. So variables in a study are any characteristic that can vary. And in our running example would be this quantitative variable that we've been looking at, systolic blood pressure. An example of a qualitative variable that could also vary from person to person is this example that we've used in the last slide, which is the type of pet a person has, so cat, dog, or fish. So with these two types of variables in mind, a hypothetical research question might be, is systolic blood pressure associated with the type of pet that you have, or that an individual in this study has? So here I've presented table 9.1 from your textbook, and it's the different types of variables and their levels of information content. So variables can be classified as nominal, so that would correspond to this level in the table. And so for instance, blood type, that would be a nominal variable, all the different blood types, A, B, O, and so forth. Color, So jaundiced versus normal skin color. Taste, bitter or sweet. So these are purely categorical variables, and hence the name nominal for naming. Okay. The second variable type of variable in this table is the binary or dichotomous variable. So for instance, heart murmur, present or absent, HIV status, positive or negative. So these are variables that can take at most two different distinct values. And these kind of variables are popular in your disease and exposure type of association studies. So presence or absence of the disease and presence or absence of the risk factor. And we're going to talk more about what kind of statistical tools and analysis would you use in order to do say assess an association between two kinds of variables that are binary. Okay, in the next highest category of variable are these so-called ordinal or ranked variables, and probably one of the most common types of ordinal variable that you may see, especially if you're working in survey data, are these Likert scale types of variables. So for instance, unsatisfied, neutral, and satisfied. So that would be a three-category ordinal variable. So the thing about ordinal variables are that the numbering actually means something here. So it's different from a categorical variable. For a categorical variable, the numbering means absolutely nothing. It only distinguishes categories, whereas for ordinal variable, the number lets you know the locations of the different values that the variable can take. So another one would be this perceived quality of care. So that would be another example of an ordinal type variable, and it could take values good, fair, poor. So you can see that there's a natural ranking of this from good all the way down to poor. In the next rung of the ladder or table, we have the so-called continuous variables. So for instance, temperature in Fahrenheit would be a continuous type of variable. And continuous variables not only let you know about the position of the different numbers that the variable can take, but it also lets you know something about the differences. So whereas, say, in an ordinal variable, the difference between good and fair might not be the same as the difference between fair and poor, in a continuous variable, the difference between 1 and 2 would be the same as the difference between 2 and 3. And finally, the type of variable with the highest information content would be the ratio variable. And essentially a ratio variable is a continuous variable, but the difference is a ratio variable has an absolute zero. So it essentially has a base point or a starting point. And temperature in Kelvin would actually be considered a ratio variable because you do have an absolute zero in the Kelvin temperature scale. Whereas in the Fahrenheit scale, zero doesn't mean absolute zero. It doesn't mean that the absence of heat. Whereas in the Kelvin scale, zero means the complete absence of heat. So for the statistical methods that we're going to use, there won't be really a difference between how we analyze ratio and continuous variables, but there definitely will be differences in how we analyze ratio and continuous variables from the types of variables that you see below. And if you look at this table, you can see the levels of information content, and I'll write a line, and the information is going from low to high in this direction. So there's more information in a continuous or ratio variable than there is in, say, a nominal variable. So let's talk a little bit more about these types of variables. So as we've mentioned, nominal variables, so nominal gets its word from the synonym naming, and these variables are categorical. As we've mentioned, their value have no measurement scale or rank order. In our pet example, the numbering cat equals 1, dog equals 2, fish equals 3 has actually nothing to do with quality. So value or importance. And so similar, we could have recoded this example as cat equals 5, dog equals 10, and fish equals 12. And the statistical analysis would be the same on this recoded data. The dichotomous or binary variables are some of the most common types of variables that we're going to encounter, and you'll probably encounter in any of the clinical research that you do. And dichotomous or binary variables are those that can assume two values, and the most common ones are whenever you're looking at the association, say, between a disease and an exposure, and one of your variables which represents the disease can either take values of the disease is present or the disease is absent, and the risk factor that you're interested in associating this disease variable with can either be present or absent. So for instance, the classical smoking lung cancer type of example, the disease would be event of lung cancer or not, and the risk factor would be smoking. So the individuals in this study would smoke or not. The thing about binary variables is, although they can only take two categories, a lot of times there is an implied direction. So for instance, normal versus abnormal, live versus dead, presence versus absence of a disease. So the direction, if a particular problem does come with a direction, that's useful for interpreting the data, but it really won't change the statistical analysis. So if you were to recode and change the ordering of these binary values, the statistical analysis would be invariant with respect to that. The conclusions would be invariant as far as the results of a test. Some binary variables don't have a direction, though. So for instance, male versus female. So sex in that case. So as we mentioned, ordinal variables are characterized by having three or more values with a clearly implied direction, and the most common ones are these Likert scale type variables. So we looked at the satisfaction of care variable earlier, and the different levels for satisfaction of care were satisfied, neutral, and not satisfied. So there's a clear ordering here of from dissatisfaction to satisfaction in this direction. And the thing about the ordinal variables is that the distance between the categories isn't necessarily the same. So for instance, the distance between satisfied and neutral is not necessarily the same as the distance between neutral and not satisfied. But however, this scale does contain more information than the nominal scale, even with that in mind. So the continuous and ratio variables, so continuous variables show both the position of different observations and the extent of the differences in value. So this is in contrast to the ordinal variables, where differences between the points really didn't necessarily mean the same thing. Here, for continuous and ratio variables, they do. So for instance, some examples would be height weight, systolic blood pressure, diastolic blood pressure, and of course more others than that. As I've mentioned, ratio variables are continuous variables with a 0 point, and the Kelvin temperature scale would be an example. So it has absolute 0, whereas the centigrade scale does not. So the Kelvin temperature scale would be considered a ratio, and the centigrade would be continuous. So another type of variable in data that we're going to be looking at are these so-called risks and proportions. You've probably looked at what risks and proportions are in some of the last EPI slides or EPI lectures, and they're a common way to look at probability, how probable is a particular event in a population. So incidence, prevalence, and measures such as that. So risks and proportions are variables computed via ratios of counts. For instance, the number of individuals with a disease divided by the total number of individuals. So that would be a ratio of counts. Since risks and proportions do share some of the attributes of both continuous and discrete variables, there will be situations where we'll look at analyzing this kind of data with statistical methods that would originally be used for continuous data, and sometimes this data is going to be analyzed via contingency table. So for instance, with a chi-square test. So I'm just write this explicitly here. So I'll say, for instance, via a chi-square test. And one of the ways to look at data like that would be to look at counts and understand what your unit of observation is. So the unit of observation is the person or thing from which the data has originated. And the most common ones in medical research, although by far this is not all, would be people, mice, cells, or other types of units. And so what we have here below is a frequency table, and this is a very common way to arrange the numbers of units that fall into cross-classified groups. So in this 2x2 contingency table, what we have is one variable, gender, and the two different levels, male and female, and we have another variable which is whether or not their cholesterol was checked. And these can be yes or no, so indicating whether or not it was checked or whether or not it was not checked. Okay, and what you see inside the contingency table in these cells are the numbers of individuals in the study that fall into each of these cross classifications. So for instance, in this cell 1-1 that I'll circle here, 17 individuals in this study were female and had their cholesterol levels checked. In this cell 1-2, 10 individuals in the study were female and did not have their cholesterol checked. Similarly, in this cell 2-1, 25 individuals were male who had their cholesterol checked, and 19 were male and did not have their cholesterol checked. So a perfectly natural question that one might want to know is, are there differences in the checking of cholesterol by male versus female? Okay, and we're going to look in chapters 11 in order to determine which method should we use in order to actually test and assess whether or not there's an association there. Okay, sometimes it's useful to combine data, and this is done routinely whenever continuous measures are converted or collapsed into certain categories. So sometimes continuous variables are converted to ordinal or binary variables according to some level of grouping. So as an example, consider body mass index, BMI. It's a continuous variable, but it's often categorized or grouped according to these classifications. So underweight would be BMI values less than 18.5. Again, these are general. This is a general uh, ordering of the BMI of the BMI measure. Of course, these would be different in different types of individuals, but in general, underweight might be categorized as BMI less than 18.5. Normal weight might be classified as BMI between 18.5 and 24.9. Overweight could be categorized as BMI between 25 and 29.9, and finally obese would be BMI values greater than 30. So the thing is, it's important to note that whenever you do this kind of collapsing or aggregation of continuous values into these kinds of this kind of ordering, you do lose information. So you have information loss, and once you do that, once you do this collapsing from a continuous variable down to some kind of ordering like this, you can't go back. You can't go back up. Of course, unless you have the original value for that measure. But if all you had was that measure, you couldn't then go back to the original continuous value for BMI. So just some conclusions for this lecture. So there are different kinds of variables, and the different kinds of variables depend on what characteristics of the values that these variables can take. Broadly, these kinds of variables, the differences in the variables are either qualitative or quantitative. And in Table 9.1 from the book, these give more specific these gives more specifics and describes the information levels of the different kinds of variables. So as we're going to see in the future chapters, understanding the kinds of variables is crucial for picking the appropriate statistical tools and analyses that you're going to do on the data. And next time we're going to discuss distributions of these variables. Thank you.